Hello student, today we will complete semiconductor electronics. In semiconductor, this is a very important chapter. If you are studying, preparing for NEET, whether for JEE or for board, it is very important. One or two questions is definitely asked in every time. We will start from energy band, then we will study intrinsic semiconductor, extrinsic semiconductor, PN junction, then usage of diode, and then finally transistor and logic gate. So dear student, what is energy band? Overlapped energy levels are known as energy bands. Energy bands in solid. During construction of solid, large number of molecules comes closer to each other. So atoms also overlapped and their energy levels also overlapped. Overlapped energy levels are termed as energy bands. This is first definition. Energy band. And from practical consideration, we assume energy band to be continuous. Overlapped energy levels are termed as energy bands and they are assumed to be continuous. Assumed to be continuous. In reality, they are not continuous, but they are assumed because separation between energy level is negligibly small. Energy bands are of two types. One is valency energy band and another is conduction energy band. What is valency energy band? And another is conduction energy band. As the name indicates, the energy band formed by the overlapping of valency energy levels is called valency energy band. In valency energy band, a large number of electrons always remains present, but still it is empty. Electron present in valency energy band do not gain energy from external electric field, so they cannot move in the free passage of crystal, and hence electron in valency energy band do not contribute in electric conduction. Electron in valency energy band do not contribute in electric conduction. Okay. What about conduction energy band? In every atom, there exists one more orbit above valency orbit, which is called conduction orbit. Electron present in conduction orbit is called conduction electron, and energy level formed by conduction electron is called conduction energy level. Usually, electrons are not present in conduction energy level or conduction energy band. But at room temperature, in case of metals, electron can easily be excited from valency energy level to conduction energy level. Okay. So dear student, if electrons are present in conduction energy band, they are free. They can accept energy from external electric field and they can move in the free passage of crystal and they can contribute in electric conduction. So what is our final conclusion? If in any solid material in conduction energy band, if electron is present, then electric conduction due to electron will take place. If electron in conduction energy band is not present, then electric conduction due to electron is just not possible, though in case of semiconductor it may take place by hole, because in semiconductor there are two agents of charge carrier, that is one is electron in conduction energy band and hole in valence energy band. Okay, but once again I am reminding you, if electron in conduction energy band is not present, means electric conduction due to electron is just not possible. Okay, so that is important conclusion. Now we are classifying solid material into three categories. We are classifying solid material into three categories: conductor, insulator, and semiconductor. Semiconductors are the materials which are having property in between insulator and conductor. Like conductivity, if we talk about conductivity of semiconductor, it is lesser than conductor and more than insulator. If we talk about resistivity, it is more than conductor and lesser than insulator. Now we are discussing important parameters on which questions are asked. First, forbidden energy gap. Based on forbidden energy gap, based on forbidden energy gap, a solid material is classified into three categories: conductor, insulator, and semiconductor. Classification of solid material. There are three bases. First, in based on forbidden energy gap. In case of conductor, value of forbidden energy gap is 0. Means in case of conductor, valency energy band and conduction energy band remains in overlapped position. If this is the picture of valency energy band minimum and valency energy band maximum. Electrons are always present in valency energy band. Now this is the picture of conduction energy band. This is conduction energy band minimum and this is conduction energy band maximum. And what about this? This is overlapped region. This is overlapped region. And remember, area of overlapping is directly proportional to conductivity. Now, dear student, what about semiconductor? In case of semiconductor, difference between valency energy band and conduction energy band is known as forbidden energy gap. This is valency energy band and this is conduction energy band. And in case of semiconductor, its order is approximately 1 electron volt. In case of germanium, it is 0.7 electron volt. In case of silicon, it is 1.1 electron volt. In valency energy band, electrons are present. In conduction energy band, no electron is there. In case of insulator, this gap is very high. In case of like diamond, it is more than 6 electron volt. So this is the first criteria to classify solid metal into three category: conductor, semiconductor, insulator. Now I am discussing second criteria. That is also very important. Many times questions has been asked in NEET and JEE. Second criteria is temperature coefficient of resistance. Temperature coefficient of resistance, that is alpha. For conductor, its value is positive. Positive indicates with the increase in temperature, conductivity of conductor will decrease. And for semiconductor, value of temperature coefficient of resistance is negative. This indicates what? With the increase of temperature, its conductivity will get increased. And what about insulator? Usually for insulator, we do not define because number of free electrons are negligible. But in case if someone insists to write, then alpha will be negative. Now, dear student, we are classifying again on third category, that is number of charge carrier. Number of free charge carrier. The agents of charge carrier in case of conductor are electrons. For semiconductor, agent is electron and hole. Electron in conduction energy band and hole in valency energy band. And another in insulator, no free charge carrier. So dear student, and if we talk about number density of free electron, this is 10 power 29 per cubic meter. Here if we talk number density of free electron, this is approximately 10 power 14 per cubic meter. This is number density of free electron. Number density means number of electron per unit volume. Here it is negligible. So dear student, this was the main criteria to classify solid metal into three categories. Now we will learn about intrinsic semiconductor. There is no 100% pure semiconductor. A semiconductor in its most purest form is called intrinsic semiconductor. Or you can say, when impurity is less than 1 in 10 power 8 ppm, when impurity concentration is less than 1 in 10 power 8 ppm, then it is called intrinsic semiconductor, or in mathematical way, This is the criteria to classify intrinsic semiconductor. To define intrinsic semiconductor, this is valency energy band, this is conduction energy band, and this is forbidden energy gap. A dear student, forbidden energy gap for intrinsic semiconductor is 1 electron volt order. For germanium, it is 0.7 electron volt because atomic number of germanium is 32. So valency electrons are present in fourth energy band. And in case of silicon, atomic number is 14. So valency electrons are present in third energy level. It is easier to detach the electron from fourth energy level to third energy level. The Fermi energy level is exactly at the midway of valency energy band and conduction energy band in case of intrinsic semiconductor. What is Fermi energy level? The energy level formed by the overlapping of energy level formed by electrons of 0 Kelvin temperature. Up to Fermi energy level, the probability of finding the electron is 50%. And another thing, how the hole is formed. When covalent bond is broken in valency energy band, then the hole is formed. How the hole is formed? And what is hole? Hole is simply the deficiency of electron. Deficiency of electron in valency energy band is called hole. It has no actual charge. It carries virtual positive charge. Of value equal to E. The mobility of hole is lesser than mobility of electron in CEB because holes are closer to the nearer to the nucleus and electrons are away from the nucleus. So mobility of hole is lesser than mobility of electron, or effective mass of hole is more than effective mass of electron. Okay. And how the hole is formed? When covalent bond is broken in valence energy band, then hole is formed. In case of intrinsic semiconductor, number of hole in valence energy band are exactly equal to number of electron in conduction energy band. Number of hole is actually exactly equal to number of electron. Number of hole in VB are exactly equal to number of electron in CEB. This is the mathematical definition of intrinsic semiconductor. Now I am telling you how the current flow takes place in the intrinsic semiconductor crystal. Mechanism of current flow. In intrinsic semiconductor crystal. In case of intrinsic semiconductor, in conduction energy band, current flow takes place due to electron. In valency energy band, it takes place due to holes. When external potential difference is applied across the ends of intrinsic semiconductor, this is conduction energy band and this is valency energy band. This is external potential difference. In the presence of external potential difference, this is high potential and this is low potential. Electron move in this direction and this is direction of motion of electron. Direction of motion of electron. And this is direction of flow of current, IE. and this is direction of motion of hole. So this is direction of hole current. So in case of intrinsic semiconductor, we write I equal to IE plus IH. Dear student, I is the electron current or IH is the hole current. Okay. Now let's see. IE equal to IE plus IH. What is IE? NE A mu E plus NH E A mu H. Dear student, what is Ne? Ne is electron density, and what is NH? NH is hole density. What is mu E? Mu is mobility of electron, and what is mu H? Mu H is mobility of hole. What is I upon A? This is cross section. This is current density. Ne E mu E plus NH E mu H. And dear student, in case of intrinsic semiconductor, electron density remains equal to hole density, that is called intrinsic charge density. Okay. So Ni equal to Ne equal to NH in case of intrinsic semiconductor. In case of intrinsic semiconductor, we write equation Nie mu E plus mu H. Dear student, if we divide J, this is current density. Remember, current density is a vector quantity, current is a scalar quantity. J upon E, E is electric field intensity. This is NI VD plus VDH. What is VD? Mu E upon E. What is VDH? Mu H upon E. What is VD? Drift velocity of electron. What is VDH? Drift velocity of hole. And what is J upon E? This is called sigma. Oh, that is wrong. This is not this. This is NEAVD. Dear student, what is current? Current is written as NEAVDE plus NHEAVDH. This VDH is the drift velocity of hole. And current upon cross section area. This is NEEVD plus NHEVDH. This is called current density, and current density upon electric field density, this is called sigma. This is conductivity, Ne mu E plus Nhe mu H. And dear student, make that correction above, okay? In case of intrinsic semiconductor, intrinsic charge density Ni equal to Nh. So what is sigma? Sigma equal to Nie mu E plus mu H. This formula is very important. And what is sigma? Sigma is 1 upon rho. Rho is resistivity. And dear student, R equal to what? Rho L upon A. So you can write rho equal to Ra upon L. This formula you can use to solve the numerical problem. So this is the equation for intrinsic semiconductor crystal. In case of intrinsic semiconductor crystal, this electron density remains equal to hole density. What is electron density? Number of electron per unit volume. What is hole density? Number of holes per unit volume. Okay, that is equal to intrinsic charge density. Now, dear student, in case of intrinsic semiconductor crystal, current flow starts when electron reaches to conduction energy band. But if we can somehow make the arrangement to start electric conduction at lower temperature, then semiconductor will behave in more better way. For starting electric conduction at lower temperature, we prepare extrinsic semiconductor. What we do? We prepare extrinsic semiconductor. How extrinsic semiconductors are prepared? By doping, by mixing some impurity. Okay, there are two types of extrinsic semiconductor. One is N-type semiconductor and another one is P-type semiconductor. Dear student, N-type semiconductor is formed when pentavalent donor impurity is formed in controlled manner. And how the P-type semiconductor crystal is formed? P-type semiconductor crystal is formed when trivalent impurity is doped in intrinsic semiconductor. Okay, trivalent impurity is also called acceptor impurity. Okay, so let's see the characteristic and formation of N-type and P-type semiconductor crystal. That is extrinsic semiconductor. Extrinsic. Extrinsic semiconductor. This is of two types. One is N-type semiconductor and another is P-type semiconductor. Dear student, what is N-type semiconductor? When impurities are doped in controlled manner. What is controlled manner? Impurity less than 1 in 10 power 6 ppm. This is medium impurity. Lesser impurity is 1 in 10 power 10 and high impurity is 1 in 10 power 2 to 10 power 4. Okay. So how the extrinsic semiconductor is formed? When in intrinsic semiconductor, crystal, pentavalent impurity, fifth group impurity, is mixed, then N-type semiconductor is formed. And when in intrinsic semiconductor crystal, trivalent impurity, third group element, then P-type semiconductor is formed. Dear student, both the type of semiconductor are neutral. Both the type of semiconductor are neutral. Okay. In case of N-type semiconductor crystal, this is also neutral. This is also neutral. You will see here majority charge carrier electron. Majority charge carrier are electrons. And here majority charge carrier are holes. Majority charge carrier are holes. Majority charge carrier always come from impurity atoms. In case of N-type semiconductor crystal, every impurity atom donates one electron in the crystal and converts into immobile positive ion. In case of P-type semiconductor crystal, every impurity atom accepts one electron and convert into immobile negative ion. Since in case of N-type semiconductor crystal, number of free electrons are equal to number of immobile positive ions. So crystal is neutral. In case of P-type semiconductor, number of holes are exactly equal to number of immobile negative ions. So crystal is again neutral. Minority charge carrier comes from, in case of N-type semiconductor crystal, minority charge carriers are holes. Minority charge carrier is always received in the crystal due to breaking of covalent bond. In case of N-type semiconductor crystal, minority charge carrier is hole. Minority. minority charge carrier are holes. While in case of p-type semiconductor crystal, minority charge carrier are electrons. Now let's see again n-type semiconductor crystal in particular. N-type semiconductor. How it is formed? When pentavalent impurity like phosphorus, arsenic, antimony is doped in controlled manner. There are three types of doping. One in 10 power 2, 2 10 power 4. This is called high doping. One in 10 power 6. This is called one impurity in 10 power 6 purity. This is called medium doping. 10 power 6 to 10 power 8. This is called medium doping. And 1 in 10 power 10. Out of 10 power 10 purity atom, 1 impurity atom. This is called low doping. If doping concentration is not given in the question, we take 1 in 10 power 6 to 1 in 10 power 8. Okay. We take medium doping. Okay. So to form n-type semiconductor, we add pentavalent impurity. In case of n-type semiconductor crystal, this is conduction energy band. This is valency energy band. Every impurity atom, because the electron, fifth electron is attached with very less energy, that is 0.03 electron volt. It is very easy to detect that. Every impurity atom donates one electron in the crystal. This is Fermi energy level in case of n-type semiconductor crystal, and this is donor energy level. Dear student, now look here. The gap is not changed due to mixing of doping. This forbidden energy gap was again same, but this gap is very less. So conduction starts at low temperature. This is 0.01 electron volt or 0.03 electron volt. In case of n-type semiconductor crystal, majority charge carriers are electrons and minority charge carriers are holes. Okay, holes are minority charge carrier. Electron is majority charge carrier. The Fermi energy level in case of n-type semiconductor is located nearer to conduction energy band. And dear student, conductivity of n-type semiconductor. Conductivity of n-type semiconductor. This is very important relation. In case of n-type semiconductor crystal, number of electron per unit volume are quite large in comparison to number of hole. So conductivity of n-type semiconductor is written as Ne mu e. This is conductivity of n-type semiconductor crystal. And dear student, remember the number of charge carrier in case of intrinsic semiconductor moving from valency energy band to conduction energy band are directly proportional to temperature of 3/2. That's why we told At zero Kelvin temperature, intrinsic semiconductor behaves as ideal insulator. While at some temperature, conductivity starts. Okay, with the increase in temperature, conductivity of semiconductor increases because here hole and electrons both remains present. Okay. Now, dear students, we will talk for P-type semiconductor. P-type semiconductor crystal. The P-type semiconductor crystal is formed when trivalent impurity is dropped in controlled manner, like boron, aluminum. Then P-type semiconductor is formed. Dear student, in case of P-type semiconductor, in case of boron, there is deficiency of one electron to complete fourth covalent bond. So every impurity atom except one electron, electron, and converts into immobile negative ion. Okay, converts into immobile negative ion. Here, in case of P-type semiconductor crystal, this is valency energy band, this is conduction energy band, this is acceptor energy level, and this is Fermi energy level, and crystal is neutral. These are the characteristics. Crystal is neutral. Why neutral? Because number of holes in equal to number of immobile negative ions. Dear student, majority charge carrier hole and minority charge carrier electron. Holes are the majority charge carriers. Holes are the majority charge carriers, and electron in conduction energy band. The majority charge carrier always comes from the impurity atom, and minority charge carrier always comes due to breaking of covalent bond in valence energy band. Electrons are minority charge carrier. They always come from breaking of covalent bond in valence energy band. And dear student, Fermi energy level remains located nearer to valency energy band. This is the criteria to classify valency, to classify P-type semiconductor, N-type semiconductor, and intrinsic semiconductor. Dear student, in case of intrinsic semiconductor, Fermi energy level remains located at the midway to VB and CB. In case of N-type semiconductor, Fermi energy level remains closer to CB. In case of P-type semiconductor crystal, Fermi energy level remains located nearer to VB. Okay. And in case of P-type semiconductor crystal, hole density is quite large in comparison to electron density. Conductivity of P-type semiconductor is written as NHE mu H to solve numerical problem. So dear student, this was all about P-type and N-type, that is extrinsic semiconductor crystal. Now we will talk our most awaited lecture, that is PN junction. What is PN junction and how it works? What are the uses of PN junction? That also we will see. One question is expected in NEET 26 from PN junction. Okay, how the use and uses, their uses. PN junction. When p-type and n-type semiconductor crystal are brought in physical contact through some crystalline process through some crystalline process, then p-n junction is formed. Dear student, we have already seen what was there in the p-type semiconductor crystal. In case of p-type semiconductor crystal, majority charge carrier are whole, and this is immobile negative ion. Here majority charge carrier are electron, and this is immobile positive ion. This is immobile positive ion. This is mobile electron, and this is majority charge carrier. And what was minority charge carrier? Here minority charge carrier was whole. This was whole. This was minority charge carrier. Dear student, in case of p-type semiconductor, whole is majority charge carrier. This is immobile negative ion. And electrons are minority charge carriers. Now, dear student, what happens when p-type and n-type semiconductor crystals are brought through some crystalline process in physical contact? What happens? Due to concentration difference, majority charge carrier starts moving towards junction. Due to concentration difference, majority charge carrier starts moving towards junction. And what happens due to movement of majority charge carrier towards junction? They start diffusing. So when diffusion of majority charge carrier takes place at the junction, here towards p side, immobile negative ion becomes surplus, and towards n side immobile positive ion becomes surplus. And what happens due to this surplus immobile ion concentration? A barrier electric field gets set up, and what this barrier electric field does, this barrier starts drifting away from the junction, due to which drift current starts. So dear student, always remember, diffusion current is due to what? Diffusion current is due to what? Diffusion current is due to majority charge carrier. And direction of diffusion current, and diffusion current remains maximum at t equal to 0. Okay, due to decrease in the concentration difference, diffusion current decreases, and drift current starts increasing because of setting of barrier electric field. What is direction? Drift current is always due to minority charge carrier. Dear student, the direction of drift current in the p-n junction is from n to p, and direction of diffusion current in p-n junction is from p to n. This is very important. Okay. So diffusion current and drift current. Dear student, diffusion current is due to diffusion of majority charge carriers. Good. and drift current is due to minority charge carrier. This is due to concentration difference. And this is due to setting up of barrier electric field. And the direction of barrier electric field at the junction is from N part of crystal to P part of crystal. You can see here. And direction of diffusion current is from P to N. And direction of drift current is from N to P. This is the diagram. This is P type, this is N type. Here is surplus ion concentration. This is direction of barrier electric field. And this is the motion of the majority charge carrier. So direction of diffusion current is from P to N. And this is the motion of the minority charge carrier. This is so direction of diffusion current is from P to N and direction of drift current is from N to P. Okay. In case of N type, minority charge carrier hole. In case of P type, minority charge carrier is electron. Because at the junction, this is high potential, this is low potential. This is the potential barrier. This is potential barrier diagram and this is electric field diagram. So dear student, a time comes when what happens? After some time, diffusion current becomes equal to drift current. When diffusion current becomes equal to drift current, then PN junction is formed. PN junction is formed. Formation of PN junction is completed. But diffusion of charge carrier do not stop, okay? It remains continue, it may remain continue, but net current through PN junction becomes zero. When PN junction is formed, net current through PN junction becomes zero. Okay. Dear student, this PN junction acts as a variable capacitor. How? See here. This is the block diagram of PN junction. It acts as a diode like this. This P type acts as positive plate of capacitor and N side acts as negative plate, and the depletion layer. What is depletion layer? This I will tell you. And depletion layer acts as a dielectric material sandwich between P and N type. So now dear student, in PN junction formation there are two important terms. One is depletion layer. This is very important term. What is there and what is not there in depletion layer? depletion layer. It is the layer of immobile ions. It is the layer of immobile ions formed near junction. Okay, it contains only immobile ions. It does not contain any free charge carrier. It contains only immobile ions. Do not contain any mobile charge carrier. Do not contain any mobile charge carrier. Okay. The approximate width of depletion layer is 0.1 micrometer, and value of barrier electric field near junction is barrier potential divided by D. Barrier potential in case of germanium crystal is 0.7 volt. In case of silicon crystal, it is 1.1 volt. So if we write something like this, so the order of barrier electric field will be something 10 to the power 6 volt upon meter at the junction. This is the approximate order. Okay. Dear student, more is the and what is width of depletion layer? It is inversely proportional to square root of doping concentration. More is the doping concentration, lesser is the depletion layer thickness, and vice versa. More is the doping concentration, lesser is the depletion layer thickness. Okay, and vice versa. Dear student, since in PN junction current flow is stopped, if you want to start current flow, then what you have to do? You have to apply potential difference across this PN junction. Okay. The manner of connecting PN junction with external source of electric field is called biasing the PN junction. The manner of connecting PN junction with external source of electric field is called biasing of PN junction. Dear student, biasing is of two types. One is forward biasing and another is reverse biasing. These are also very, very important from Neet 26 point of view. So let's learn what is forward biasing and what is the effect of forward biasing, what is reverse biasing and what is effect of reverse biasing. Let's see. Biasing of PN junction. First, what is biasing? Connecting PN junction with external electric field is called biasing. Dear student, biasing is of two types. One is forward biasing and another one is reverse biasing. In case of forward biasing, when P part of a crystal is connected to the positive terminal of the battery and N part is connected to the negative terminal of the battery, then PN junction is said to be in forward bias. Okay. And what is reverse biasing? When P part of a crystal is connected to negative terminal and N part of a crystal is connected to positive terminal of battery, then PN junction is said to be in reverse bias. Okay. Now, dear students, we will see effect of forward biasing and effect of reverse biasing. This is the simple diagram of forward biasing. This is forward biasing. And this is the diagram for reverse biasing. The P part is connected to positive terminal of the battery and N part is connected to negative terminal of the battery. Okay. This is forward biasing. And when P part is connected to negative terminal of the battery and N part is connected to positive terminal of the battery, this is reverse biasing. Okay. Now, dear student, you can easily see under the influence of forward biasing, what will happen? Majority charge carrier will start moving towards junction. And under the influence of reverse biasing, what will happen? Majority charge carrier will start moving away from the junction. Okay. While minority charge carrier will start moving towards junction. Okay. In case of reverse biasing, majority charge carrier will start moving away from the junction and minority charge carrier will start moving towards junction. Okay. So, dear student, what will be the effect of forward biasing? Forward biasing of PN junction. Dear student, under the influence of forward biasing, majority charge carrier starts moving towards junction. This is barrier electric field and this is external electric field. So barrier electric field at junction decreases, barrier potential decreases. There may be some numerical problem in this. Suppose electron here has velocity v1 and here electron has velocity v2 and voltage drop is vb. So what you will be writing the equation? Half mv1 square equal to half mv2 square plus EVB. This equation you can use from energy conservation point of view. So barrier electric field decreases, barrier potential decreases, depletion layer thickness decreases. Here in junction resistance in forward biasing, this is change in forward voltage divided by change in forward current. This remains of the order of kilo ohm and current remains of the order of milliampere. And this is the equation in case of forward biasing. I equal to I naught is reverse saturation current e power qv upon kt minus 1. In case of forward biasing, e power qv upon kt is quite large in comparison to 1. So I can be written as approximately I naught e power qv upon kt. K is Boltzmann constant here. Dear student, here one term is very important, that is knee voltage. In case of forward biasing, one term is very important, that is called knee voltage. What is knee voltage? For germanium, it is 0.3 volt. For silicon, it is 0.7 volt. Knee voltage is the voltage in forward biasing till current increases with voltage in a linear way. Okay. This is forward current. This is forward voltage. And after that, current shoot up in exponential way. This is knee voltage. Okay, the voltage is the voltage in forward biasing till current varies with voltage in a linear way. After that, growth of current is exponential. Okay. So, dear student, this was all about the forward biasing. And in case of forward biasing, ideal diode, this PN junction acts as a diode. And in forward biasing, it acts as a connecting wire. In forward biasing, the resistance of ideal diode is 0. In case of forward biasing, the resistance of ideal diode is 0. Okay. Now, dear student, let's see the reverse biasing. Reverse biasing of PN junction. See, in case of reverse biasing, what we do? When P part of a crystal is connected to negative terminal and N part of a crystal is connected to positive terminal of the battery, then PN junction is said to be in reverse biasing. In the effect of reverse biasing, majority charge carrier starts moving away from junction and minority charge carrier starts moving towards junction. So dear student, this was the direction of barrier electric field at junction. This is the direction of applied electric field at junction. So what happens when PN junction is connected in reverse biasing? Under the influence of reverse biasing, barrier electric field increases, barrier potential increases, depletion air thickness increases, junction resistance increases, that is delta VR upon delta IR, change in reverse voltage upon change in reverse current, and this remains of mega ohm in germanium crystal and giga ohm in case of silicon crystal. The current remains of the order of microampere in case of germanium crystal, nanoampere in case of silicon crystal. Okay. And in case of reverse biasing, if we increase the applied voltage, a stage may also come when diode gets fail. Okay. The diode may get failed due to two reasons. One is due to Zener breakdown, another due to avalanche breakdown. That is also very important. Due to application of potential difference, the value of barrier electrode becomes so high that large number of covalent bond is broken at the junction. If the diode is getting broken, due to setting above very high electric field at the junction, and due to that large number of covalent bond are broken at the junction, then diode gets failed. This is called Zener breakdown. Okay. This is called Zener breakdown. And what is avalanche breakdown? This reverse biasing of PN junction acts as a forward biasing for minority charge carrier. So the minority charge carrier starts moving towards junction and they collide with the covalent bond in the crystal, and due to which charge carrier liberated. So avalanche breakdown is due to collision ionization, and Zener breakdown is due to what? Barrier electric field. Okay. To save the diode from breakdown, in reverse biasing we use a special diode, that is Zener diode. Okay. That is a heavily doped diode. Depletion thickness remains low when doping is high. Zener diode is used. Zener diode is a special diode which is prepared to keep diode safe in reverse biasing. It works only in reverse biasing. Works only in reverse biasing. Doping is high. Depletion thickness is less. The symbol of Zener diode is like this. This is Z shape. This is P side, N side. Dear student, when voltage drop at load is less than Zener voltage, this diode do not work. It acts as open circuit. In reverse biasing. In forward biasing, it acts as a normal diode. But when voltage drop at the load is greater than or equal to Vz, then it stabilizes the voltage. Okay, it is called voltage stabilizer. Voltage stabilizer. It will work only in a situation when voltage drop at the load is either greater than or equal to Zener voltage. So it will maintain the Zener voltage. Okay, it will maintain. How? This is also very important for NEET 26 question. May 99% chances are there that some question may come on application of Zener. Let's see here. This is the applied voltage. This is input resistance. And this is Zener diode connected in reverse biasing. P is connected to negative, N is connected to positive. And this is load resistance. Dear student, this is input current, this is Zener current, and this is load current. If voltage drop at load is greater than equal to Vz, then this equation you can apply by applying KVL. V minus Vz equal to I input into Ri. Here you can find I input. In parallel, voltage drop remains same, so Vz equal to I L into RL. From here you can find IL. And now, dear student, from Kirchhoff junction law, you can find Zener current equal to I input minus I load current. Okay. But if V is less than Vz, the circuit will be only this. Because it will become open circuit. And dear student, if the diode is connected in forward biasing, this Zener diode, it will act as a simple diode. Okay, so this is the important thing. Okay, this is very important point for Zener diode and to solve the problems. Okay. Now, dear student, there are many types of diode. The important points about diode I am telling you. In reverse biasing, for ideal diode, resistance becomes infinity. It acts as a broken wire. Okay. First is light emitting diode. Second is photodiode. Third one is solar cell. The light emitting diode acts in forward bias. photodiode acts in reverse bias, and here unbiased. This is the symbol diagram of the LED. This is the symbol diagram of the photodiode. Dear student, when forward current is applied, starts flowing in the LED. Based on the semiconductor material used, light emitting diode gives the colors, different colors, okay? In case of LED, the forward energy gap remains in the range of 1.8 electron volt to 3 electron volt. This is the range of forbidden energy gap. When forward current starts flowing in the circuit, recombination of electron and hole at the junction starts. Recombination of electron and hole starts at the junction. So what happens? When recombination of electron and hole starts at the junction, electron in conduction energy band makes transition to hole in the valency energy band and energy is liberated. Based on the amount of energy liberated, that also depends on the type of semiconductor material used, light is emitted, okay? So there are different type of LED, white, red, orange, blue, okay? Many types of LED. Now, dear student, let's see working of photodiode. In case of photodiode, when energy of photon remains greater than equal to forbidden energy gap, then extra current starts flowing in the circuit. And with the increase in intensity, current increases. I3 greater than I2 greater than I1. This is dark current. And what about the solar cell? In case of solar cell, first thing is it is unbiased, and second its diagram that may be asked in the exam. This is open circuit voltage. This is short circuit current. So dear student, this was all about the working of PN junction, and let's see some more example for the diode. Suppose this is ideal diode. This is battery. This is 4 ohm and this is 2 ohm. So in case of ideal diode in forward biasing, how you've seen the forward biasing? Because P part is connected with the positive terminal. So in case of ideal diode, forward biasing resistance will be 0. I will be equal to V upon R. This is 4 volt. So current will be 2 ampere. Okay. While in case of reverse biasing, suppose this is the diagram. Here current in the circuit will be 6 upon 3, that is 2 ampere. No current will flow through the diode because it is in reverse biasing. Okay. So this is how we will apply in numerical problems. Dear student, there is one very important application of diode, that is as a rectifier. As a rectifier. Diode as a rectifier. What is rectifier? A rectifier is an apparatus to convert alternating current into direct current. Apparatus converting alternating current into direct current is known as rectifier, okay, and the process is called rectification. Dear student, there are two types of rectifier. One is half wave rectifier and another is full wave rectifier, okay. In case of rectifier, in the output of rectifier, in the output of rectifier, we get impure DC. That is, we obtain pulsating DC. Pulsating DC means DC remains mixed with the AC. DC remains mixed with AC. This AC, presence of AC in the output of rectifier is called ripple. Presence of AC in the output of rectifier is called ripple. To remove this ripple, we may use filter circuit. Made up of L or C or combination. The best filter circuit to ripple control is pi filter. Pi filter is best filter for ripple control. And the choke input filter is a voltage regulator. Now, dear student, let's learn about ripple factor. Ripple factor is written as IAC upon IDC. This can be written as IRMS upon IDC whole square minus 1. How? Dear student, for half wave rectifier, IRMS equal to I0 upon 2, I0 is peak value, and IDC equal to I0 upon pi. So half wave rectifier gives us R equal to 1.21. So in case of half wave rectifier, presence of impurity remains more than presence of purity, okay. IAC is more than IDC. For full wave rectifier, IRMS equal to I0 upon root 2 and IDC equal to 2I0 upon pi. Here ripple factor is 0.4. So dear student, AC is present in both the type of rectifier. But here in full wave rectifier, impurity is less than purity, okay. And here impurity is more than purity. So this is also important parameter for rectifier and rectification. Now we will see working of half wave rectifier and full wave rectifier. One very important term also, let's see, that is ripple frequency. If omega is the frequency of input AC signal, so by Fourier analysis, the dominant ripple frequency in half wave rectifier is omega, and dominant ripple frequency In full wave rectifier, this is 2 omega. Though frequency in decreasing amplitude are omega, 2 omega, 4 omega, 8 omega, like this. Here 2 omega, 4 omega, 6 omega, like this. But they are in decreasing amplitude. Dominating ripple is 2 omega. Means if input frequency is 50 hertz, then ripple frequency in full wave rectifier will be 100 hertz. Dominant ripple frequency in half wave rectifier will again be 50 hertz. Okay. Dear student, now look at the working of half wave rectifier. Working of half wave rectifier. As the name indicates, only one half part of input AC signal will be converted to DC signal. This is primary of transformer, this is secondary coil of transformer, and this is the diode. And output signal is received across load resistance. Dear student, for the first half part of input signal, this is input AC signal. This is first half part, this is positive, second half part is negative. For the first half part, this point A remains positive and B remains negative, means diode works. Diode converts AC to DC. For the second half part of input AC signal, A comes negative and B comes positive, so diode remains in reverse bias. So peak inverse voltage takes place. Peak inverse voltage of value V0 takes place at the diode. Okay. So peak inverse voltage in case of half wave rectifier is V0. So if this is input AC signal, then this is output DC signal, but this is not pure DC, this is pulsating DC. Only one half part of input AC signal is converted to DC signal. Okay. Dear student, now we are working for full wave rectifier. Working of full wave rectifier. This is the diagram of full wave rectifier. This is input AC signal. This is one diode. This is centrally tapped transformer, which maintains the phase difference of pi, and output signal is obtained across load resistance RL. This is diode D1 and this is diode D2. Dear student, for the first half part of input AC signal, this is first half part, this is second half part. For the first half part of input AC signal, what happens? For first half part of input AC signal, A remains positive, B remains negative. So D1 remains in forward bias, D2 remains in reverse bias. So D1 converts AC to DC, and here peak inverse voltage takes place. For the second half part, for input AC signal, A becomes negative, B becomes positive. So D1 becomes reverse bias, D2 becomes forward bias. So peak inverse voltage takes place here. That is equal to V0, and diode D2 for this converts AC into DC. So dear student, in this full wave rectifier, both the part of input AC signal is converted into DC signal. Okay. Now see here. This is direction of current flow, this is direction of current flow. And the output signal is obtained across load resistance, okay? So here, if this was the diagram of input AC signal, then this is the diagram of output DC signal. This is due to D1, this is due to D1, this is due to D2, this is due to D2. So dear student, so whether you use half wave rectifier or full wave rectifier, whether you use half wave rectifier or full wave rectifier, in both the rectifier, in the output of rectifier, you will get pulsating DC, means AC will remain mixed in the DC. The presence of AC, as I told you earlier, presence of AC in the output of rectifier is called impurity, that is ripple, okay? If you want to remove ripple, you have to use filters made up of inductor or capacitor, LC. How the LC filter works? Look at the working principle of filter. Filter circuit. Dear student, if you see pure DC, for pure DC, omega equal to 0. So inductive reactance equal to 0 and capacitive reactance remains infinity. So if you pass AC and mixture of AC and DC, so here what will pass? DC will pass and here low frequency AC will also pass. If you pass, if you apply capacitor and pass AC and DC mixture, so what will happen? Only DC will pass, because for AC resistance will be infinity, okay? So this is how we can separate DC and AC through filter circuit. This is how we can separate DC and AC through filter circuit, okay? Now dear student, this was all about the diode classification, and now we will see about the transistor. The name transistor means transfer plus resistor equal to transistor. Transfer plus resistor equal to transistor, okay? Means a transistor is a device, they transfer. A transistor is a device, they transfer emitter current, that transfers emitter current from low impedance zone to high impedance zone as collector current, okay? Transistor is a current driven device, they transfer emitter current as collector current from low impedance zone to high impedance region. Transfer plus resistor equal to transistor. Dear student, transistors are made up of three doped semiconductor regions discovered by Bardeen, Baratain and Shockley. Transistors were discovered by Bardeen, Baratain and Shockley. Transistors are made up of three doped semiconductor region. They are of three types. There are two types. One is NPN and another one is PNP. In every transistor, first part is called emitter, second part is base and third part is collector. First part is emitter, second part is base, third part is collector. In NPN transistor, the role of emitter is to transfer the electron from emitter to base. Role of base is to receive the electron from emitter and transfer them to collector. And role of collector is to collect the electron from base zone. And in PNP transistor, role of the emitter is to transfer the hole from emitter zone to base zone. And role of base is to collect the holes from emitter zone and transfer them to collector zone. And role of the collector is to receive the holes. Okay. Maximum doping is done in emitter, then lesser doping is done in collector, and base is thinly doped. The surface area of collector remains maximum, then emitter, then base. Okay, base is thin. In case of NPN transistor, NPN, in case of PNP transistor, this is emitter, this is base, this is collector. Direction of conventional current in case of PNP transistor is from emitter to base. And here this is emitter, base, collector. This is from base to emitter. Dear student, now let's see the working of NPN transistor. Now let's see the working of NPN transistor. This is N, this is P, this is N, this is emitter, this is base, this is collector. Always remember, to keep the transistor in active mode, emitter junction is always given forward biasing and collector junction is always given reverse biasing. If emitter is given reverse biasing, collector is given forward biasing, then the transistor action will become inverted. If emitter junction and collector junction both are given forward biasing, then transistor becomes saturated. If emitter and collector junction both are given reverse biasing, then transistor action becomes off. Okay. So dear student, to keep the transistor in active mode, the emitter junction is given forward biasing, N is connected to negative terminal, and the collector junction is given reverse biasing, the N is connected to positive terminal. This is emitter base battery, this is collector base battery. Both the batteries are of low voltage, but collector base battery is more voltage than emitter base battery. Under the influence of forward biasing, this majority charge carrier starts moving towards junction. And less than 1% electron hole diffuses at the junction, and more than 99% electrons, more than 99% electrons are attracted by this VCB battery. Okay. When one electron diffuses with one hole at the junction, so in N part of the crystal, one electron decreases, in P part of the crystal, one hole decreases. So to fill this deficiency of one electron from negative terminal of the battery, one electron move from here, one electron is moving from here, the current starts here. Here, when one hole is becomes deficient, to fill the deficiency of one hole, what happens? Then one covalent bond break and one electron move here, then current here. This is IB. And when electron reaches here, electron passing here, then current is here. This is, so at the junction, what is IE equal to IB plus IC? IC upon I is called current transfer ratio. This is general equation of transistor. IE equal to IB plus IC. IB remains very less than IC. IC upon IE is known as current transfer ratio. Dear student, In NPN transistor, both inside and outside the crystal, current flow is due to electron. And the direction of conventional current is from base to emitter. Is from base to emitter. As we have shown earlier. This is NPN. This is emitter. This is base. This is collector. So in case of NPN transistor, direction of conventional current is from base to emitter. Okay. Now, dear student, let's see working of PNP transistor. Working of PNP transistor. To keep transistor in active mode, first junction, emitter junction is given forward biasing. P is connected to positive terminal. Here P is connected to negative terminal. Reverse biasing. This VCB is remains more than VEB. Under the influence of forward biasing, this majority charge carrier starts moving towards junction. Since VCB is more than VEB, so more than 99% holes reaches to collector zones. So what happens? Under the influence of forward biasing, these majority charge carrier moving like this. So inside the crystal, current flow is taking place due to holes, and outside the crystal, current flow is due to electron. How? When from P part of crystal, N part of crystal is here one electron diffuses, to fill the deficiency of one electron from negative terminal of the battery, one electron move from here, the current starts from here like this. When one hole diffuses at the junction, to fill the deficiency of one hole, what happens? One electron here, so current move like this. And this is again IC. So again I equal to what? IB plus IC. IB remains very less than IC, and IC upon I is current transfer ratio. Okay. So inside the crystal, current flow is due to hole. And direction of conventional current is from emitter to base. This is very important. This remains little lesser than, little away from the collector, because area of collector remains more. So this is not at the center. This is PNP. This is emitter. This is base. This is collector. This is emitter current. So dear student, NPN transistor works better than PNP transistor because mobility of electrons remains more than mobility of holes. Okay. Now dear students, we will look something for logic gates, digital electronics. Okay. A scientist named as George Boole defined Boolean algebra. There are two terms, one is high, another one is low. Too high he wrote 1, too low he wrote 0. Okay, like that. And he gave some expression to solve digital electronics problems like this. Here 1 plus 0 remains 1, 0 plus 1 remains 1, 0 plus 0 remains 0, and 1 plus 1 remains 1. And 1 dot 0, this remains 0, 0 dot 1, this remains 0, 0 dot 0, this remains 0, 1 dot 1, this remains 1. A bar means A. And this is De Moivre theorem. In digital electronics. A plus B bar, this can be written as A bar dot B bar. A dot B bar, this can be written as A bar plus B bar. Now, dear student, there are three types of, one is truth table. What is truth table? A table showing all possible combinations. A table showing all possible combinations of input and output is called truth table. Okay. Input and output combination table. Now, dear student, there are three basic gates. One is OR gate. This is the symbol diagram. Here are two inputs and one output. And Boolean expression is A plus B. Now you can write the truth table, very simple. A, B, Y. 1, 1, 1. 1, 0, 1. 0, 1, 1. 0, 0, 0. So in the output of OR gate, we will get 0 when it's both the input are 0. Okay, this is truth table for OR gate. Now, dear student, let's see about the AND gate. The Boolean expression for AND gate is A dot B, and this is the diagram. There are two inputs and one output, A, B. The Boolean expression, the truth table is like this. This is A, this is B, and this is Y. This is 1, 1, 1, 0, 1, 0, 1, 0, 0. 0, 0, 0. In the output of AND gate, we will get 1 when it's both the input are 1. And NOT gate. This is normally used in stairs. The symbol diagram for NOT gate is like this. Here is only one input, A, and Y equal to A bar. So input is 1, output is 0, input is 0, output is 1. When in the input it is low, it is in the output it will be high. In the input it is high, in the output it will be low. Now, dear student, from the basic gates we prepare other gates also. Now let's see NAND gate. NAND gate means what? AND plus NOT. That is NAND gate. Very simple. This is AND gate. Right here G0 type. This is NAND gate. Here two input and the Boolean expression for NAND gate is A dot B bar. From De Moivre theorem, you can write this like this, A bar plus B bar also. If you want to write the truth table A, B, A dot B and Y. This is 1, this is 1, this is 1, this is 0. Because Y is what? A dot B bar. This is 1, 0, 0. This is 1, 0, 1, 0, 1, 0, 0, 0, 1. So in the output of NAND gate, we will get 0 when it's both the input are 1. Now let's see NOR gate. NOR gate is OR plus NOT. Is in NOR gate. This is the pictorial diagram. There are two input, and this is Boolean expression a plus b bar. This you can write as a bar dot b bar also from de Broglie theorem. This is truth table a b a plus b and a plus b bar. Okay. Now 1 1 1 0 1 0 1 0 0 1 1 0 0 0 0 1. In the output of NOR gate, we will get 1 when it's both the input are 0. When it's both the input are 0. Okay. So this is the result of the NOR gate. So dear student, this was all about the semiconductor electronics. In the next lecture, we will see many problems in semiconductor electronics. Keep following our YouTube channel M.Tech Kota. If you are interested in finding the lectures, very important lectures and marks maximizer practice sheet with the support of those, you can easily score 180 out of 180 in physics. And there are many test series, very NTA based good test series also there. So you download the app M.Tech from Google Play Store and secure and safe, make you safe your journey. Thank you, students.